Excellent. Okay, 89% of you get 12.4 nanometers. Yawn. Why is that important? Wait a second. What did we just say? 12.4 nanometers. This is like 10 times bigger than an atom, right? But we just said on the previous slide, there's a solution. On this slide, we said that the answer was 0.123 nanometers. Wait a second. Both the electron and the photon here had 100 electron volts of energy. But the electron has way, way smaller wavelength, like 100 times smaller. What's with that? And what's waving after all? What's going on? How can we talk about particles really being a wave? What does this mean? So we have this de Broglie relationship, P equals h over lambda, but it gives us a very different wavelength for an electron with kinetic energy 100 electron volts, or a photon with energy 100 electron volts. And I think the idea is that when a particle has mass, sort of the presence of that mass, when you actually work it out, if you do it all properly and relativity and everything else, you're going to find that the wavelength corresponds to a much shorter wavelength for a massive particle. And if it were a proton, it would be, another factor of 2,000 times shorter wavelength than for a photon. That's just the way it works out in nature. Now, when we take that equation written down by Schrödinger, this three-dimensional wave equation, and solve it for the standing wave patterns of electrons orbiting a proton, this is what we see. Now, when we draw these pictures, they're a little bit unsatisfying because they don't really show you the full three-dimensionality. We're just taking a slice through the pattern for different sets of quantum numbers. You'll see each of these is labeled by 3 numbers, which you might have encountered in chemistry. But they correspond to, the first number corresponds to the energy level that we already saw, the Rydberg energy levels, the same energy levels as in the Bohr atom. And the answer turns out to be exactly the same as what Bohr got with his model for the energy levels. What was new in the solutions to the Schrödinger equation is that you have additional quantum numbers corresponding to the angular momentum of the electrons going around the proton, and the so-called total angular momentum and the z component of the angular momentum. There turn out to be 3 numbers which characterize every solution to the Schrödinger equation for hydrogen. And I think they are often called N, L, and M. And N is the energy level number, so you see 2, 3s, 4s down here. And as you get to higher and higher angular momentum states and higher energy states, you see more and more complex patterns forming. So, for example, this one, the 2, 1, 0 state, is actually 2 blobs on top and on bottom, meaning you tend to find the electron here or here, but not out here. Whereas these radially symmetric ones, you have sort of shells in which it's likely to find the electron at a small radius or a larger radius. For n equals 3, there are 3 different radii at which you can find it. N equals 4, there are 4 different radii, etc. So you could think of the dark rings in between these as being the nodes of the standing wave, and antinodes are the bright spots here where you tend to find the electron. When you have this one, for example, I believe it's a sort of a donut ring on the top and the bottom. But you have this one, there's 2 lobes and then a ring around it. They're really beautiful and intricate patterns that are created by these, by the solutions to the Schrödinger equation. The real question, though, is what is waving? And we'll get to that in a minute. The great thing was that once we had this, once we were able to predict the structure of electrons, we were able to unravel at last the structure of the periodic table. Why does it have this bizarre shape, with all these atomic species lining up in columns like that and hydrogen-like ones here? Well, it turns out that any element any atomic element in this column is hydrogen-like in the sense that there's one outer electron orbiting a nucleus and or the other electrons in it as if it were. So these are all hydrogen-like things: hydrogen, lithium, sodium, potassium, rubidium, etc. Whereas these noble elements have filled atomic shells. Atomic shell means an energy level, and an energy level can contain only a certain number of electrons. So when that number is filled, 2, 10, 18, 36, then the atom doesn't have any free or semi-free outer electrons to bond with others. That's why these elements are the noble gases, for example. And if you have a tank of, let's say, xenon, it's in its atomic form, this doesn't form xenon molecules, unlike hydrogen, etc. So once we understood that, of course, then we understood a great deal about chemistry and solid-state physics and all of the technology we now enjoy, and these advanced materials which people are creating and doing wonderful things with was laid open for us, as well as understanding of the heavy elements and nuclear physics and nuclear energy, nuclear chemistry, medicine.